Hello everyone, welcome. My name is Suresh Sugumar, and then today I'm going to give you an overview of zero trust and how we can apply that principles to RISC-V system. So I work for TII, it's Technology Innovation Institute. It's a premier research institute in ATRC. It's a research wing that has several research centers, and one among that is Security Systems Research Center, where I belong. We drive zero trust, end-to-end security and resilience for both cyber physical and autonomous systems. And in specific, I work on drone platforms. What is zero trust? Traditionally, in a networking sense, the term was coined back in 2010 by Forrester. It's a new security framework built around the concept of never trust and always verify. Let's see what that means. On the left, you see the circle. Inside is the implicit trust zone where everybody is already trusted, and anybody outside will need to be verified. The problem with this, if you have an insider attack, you can't do much. That's why that transition happened where the circle of trust was broken, and anybody and everybody has to be authenticated and verified. So this is much smaller implicit trust zone. Insider attacks can be mitigated. That's the whole thing about zero trust. Zero trust doesn't mean no trust. In fact, quite the opposite. Here, this is a network of nodes and devices connected either wired or wireless, right? Next is a drone system, which has a bunch of components connected on the motherboard or a PCB. Do you spot a commonality here? I see that a bunch of nodes are connected here, a bunch of things are connected here. It has an SoC where a ton of IPs are interconnected using a network on chip. And it runs software. Software has its own relationships and connectivity. So if the network has adopted zero trust principles, can we also adopt for the system shown here? That's the topic we will explore in detail today. What are those zero trust principles? There are 10 principles. We will walk through a few, and you can go to the link and then understand more about it. Verify explicitly is the first one, where every access should be explicitly verified without any trust assumptions. Least privilege, a subject should be only given those privileges to carry out that particular task and nothing more. Fail securely, ensure that error conditions don't leave the secrets around. For example, if there's a cold boot attack, somebody could snoop the data that is still in the memory or whatever it is, and then that's bad. Complete mediation, unless a subject is given explicit access to an object, it should be denied the access. Secure the weak link, protect the weakest link in the chain. It's pretty obvious, ending with simplicity. So these are the principles. And we will see what's the platform at a high level. This is a drone platform as a reference for this discussion, where you have a cloud that dispatches missions, and the missions are processed in the mission computer, which is a chip in the platform. And it communicates with the flight controller, which actually manages the flight to carry out the operation. Flight controller actually gets information from these sensors, and then in turn gives output for the motors to operate, what speed, what altitude, how fast it should go to carry out that operation. It's not a surprise that pretty soon we're going to see pizzas delivered to your homes with drones. I see that these devices are going to be multi-tenanted, where there'll be service providers where they offer the drones, and there are customers who would put their applications on top. For example, a pizza delivery store, a medicine delivery store, and they could have multiple apps running at the same time. Applying zero trust principles to a drone system. We'll take a look at it and then see some examples. So if you translate the drone system into a stack-like structure, bottom is hardware and platforms, then you have the middleware, and then you have the applications on the top. There are implicit trust relationships here. So if you spot it, like the application trusts the VM, trusts the hypervisor, even trusts the hardware for it to execute its mission correctly. Let's take another example with the TE. If the TE has to offer confidentiality and integrity to its the application what is running on top, it needs to rely on hardware functions like MMUs, MPUs, IOMMUs for offering those memory protections and stuff. Let's take a look at few examples and see if there is an opportunity to modify or alter these trust relationships for the better. We'll take a look at the first example, protecting your code and data that is in use. So we pretty much know that we use encryption for code and data that's at rest on your device. And then when they are in transit on the network, you also encrypt. But what about the things in use? Other architectures like x86 and ARM do have this capability, but we need to build it for RISC-V. The code and data that's running on the platform needs confidentiality and integrity protection. We don't want somebody to come in and snoop information that's top secret, whatever things. So the idea would be to use the TEs to offer confidentiality and integrity for the code and data. It could be at the VM level, it could be at the application level, or it could be at the data level. So there are terms in the industry called confidential VM, confidential data enclave, confidential application enclave. These all fall into the category of confidential computing. The beauty of this is it offers a remote verifier to attest the platform. Is my platform running good? Is my application and data confidentiality and integrity protected? To gain that trust. So from a RISC-V point of view, when we develop the confidential computing, we need to ensure all these interfaces from the hardware device side are compatible with the existing TE standards or TE providers' expectations. So that way we can gel well into the ecosystem. Control flow alteration. So you might have heard of the things like buffer overflow and code injection attacks have been happening for almost 2 decades already, where somebody corrupts the stack, and then when your code returns back from its function, it just jumps to somewhere else, as you see here. So typically, some of the other architectures use something called shadow stack. It is just one solution. There are many other solutions. So this looks very promising for RISC-V as well, where you will have a shadow stack that always checks the return values and the stack pops and pushes. And if there is a mismatch, it fires an exception. Let's look at another one where it's a forward jump, where you call a jump to a function. For example, you are here and you want to jump to the test function, and typically you will jump here. But there could be corruption. Somebody could tamper the pointers and then ask you to jump to somewhere else, not at the beginning of the function, but right in the middle of a function to avoid or to bypass something. This is also not good. What we sort of think is called landing sites, where at the beginning of every function, you will have a landing site instruction or a label sort of thing where the hardware can check when a jump occurs, is it legit? If this instruction is not the next instruction after the jump, you know for sure something went wrong and you cause an exception. Also, you can have a label attached to this landing site instruction where the labels can also defend you against corruption attacks. Another one is still related to TE. TEs today are fixed at design time, so they don't adapt to changes like new devices being attached to your device or your platform, or removal of USB, attaching another USB device. It only can offer strong security guarantees for code and data on the CPU. It does not do for the peripherals. So if you want to attach a peripheral to your TE, today you have to rely on untrusted software. Can we change that? So this is the state of the art. and peripherals like this are out of your enclave. When your TE extends to support these peripherals, this is something like, this is the way it will look. The flash memory, 5G, all these PCI devices and SPI devices are also part of your enclave. A rogue device or IP on your platform. So how do you know there is a rogue device or a rogue IP in your system? For example, when you receive a message on the NOC, how do you know it's coming from a right party? Is the message valid or legit? Today we simply assume anything connected on the hardware is all good things, right? So, and things like how do you know a GPU module that is attached to your platform has the right initial firmware put by the manufacturer and not tampered? So today it's complex and there is no way you can do. So there are two industry consortiums, Open Compute and DMTF. They are working on standards for developing mutual authentication between these components and IPs, where an initiator could poll a component to verify, basically, to ask for certificates, to send a challenge and response to make sure I'm talking to a legit device on the other side, verify the component is genuine, verify the firmware is correct as published by the manufacturer, and then finally establish trusted link by authenticated and encrypted data transfer links. So as an example is a PCI SIG integrity and data encryption standard where the links are protected and thereby you verify and trust and not by assumptions. So once this is established, you can trust the other device. Finally, we will finish with the supply chain vulnerabilities where a design house today ships a design to a factory. Let's say it's a untrusted foundry, and then you don't know for sure. There could be IP theft, there could be counterfeiting and overbuilding that might be happening, and you don't know. So there has been a research going on for many years, and then finally I think it's time for maturing that mechanism which is called logic locking, similar to password-based protection of your software or like a key for unlocking your operating system disk. Logic locking is basically a stream of bits that you generate and lock your hardware. You ship it out to the factory. So as long as it's outside your perimeter, the chip is basically locked because nobody has the password. Only you know the password. And then it gets manufactured and then it comes back to you, and then you put in those passwords that you know to unlock it and making it a working chip. So this sort of protects any attack that goes through which is outside your control of influence. So that concludes some ideas for discussion here. I would like to summarize here, mentioning zero trust is key in achieving all-round security for any platform. We are collaborating with many of our research partners, RISC-V.org, and several consortiums to bring. So if you are interested in contributing to zero trust technologies for RISC-V, you can hit this link and then you can join in. So thank you very much. It's been a pleasure sharing ideas with you guys. If you have any questions, please feel free to send an email to me. Thank you very much. Have a good day.